We're going to take a look at the control of hormone levels in the blood, abnormal secretion of hormones, and hormone interactions in this video. There are several things that control the release of hormones. There can be neural signals for some hormones that stimulate their release. So for example, cortisol release is stimulated by stress. Circadian rhythms are involved in stimulating the release of some hormones. So for example, growth hormone. Circadian rhythms are coming from the hypothalamus. There's a certain group of neurons in what's called the suprachiasmatic nucleus. You don't need to memorize that. And then also from melatonin. Remember, that hormone is secreted by the pineal gland that's in the brain. So that's also involved in controlling the circadian rhythm, those 24-hour cycles. And then humoral signals. Humors is an old term for body fluids, or in this case talking about the blood. So other hormones, so for example, hypothalamic hormones can control the release of the anterior pituitary hormones. And then ions and nutrients can control the release of some hormones. And then negative feedback is used a lot to control hormone release. And then in a few instances, positive feedback is used. Here's an example of neural control of hormone release. So we have stress that will stimulate the hypothalamus to release CRH, which will then go to the anterior pituitary, release ACTH, which then goes to the adrenal cortex to stimulate the release of cortisol to help you deal with the stress. Negative feedback loops from hormones do a lot to keep hormone levels in the normal range. So for example, cortisol will have a negative feedback effect on the anterior pituitary and hypothalamus. And that will affect the secretion of CRH and ACTH to make sure that we keep the cortisol levels in the normal range. And then we can have some negative feedback loops from other signals in the blood. So for example, some nutrients like glucose. That can have a negative feedback effect on the pancreas. And when the blood glucose levels are getting too low, that will feed back on the pancreas and say, hey, we don't need any more insulin being secreted. And then for aldosterone, hormone also coming from the adrenal cortex, aldosterone can be stimulated by high potassium levels in the blood. And when the potassium levels get low enough, that will have a negative feedback effect on the adrenal cortex and say, hey, we don't need any more aldosterone secreted because our blood potassium levels are low enough that we don't need any more aldosterone secreted. And then in some cases, we do have positive feedback loops with some hormones. So remember we talked about that with the LH surge. So remember that positive feedback will push things further away from the normal range. And then there's usually some way to shut off the positive feedback loop, and then things will go back down to normal again. So in the case of the LH surge, ovulation is what shuts off that positive feedback loop. Another hormone that's under positive feedback control would be oxytocin during childbirth. There are a couple things that control the hormone levels in the blood. So first is how fast or the rate of hormone secretion, which is controlled by the things that we were just talking about. And then the amount of hormone that's bound to the carrier proteins. So remember that only the unbound hormone can bind to the target cell receptor. And remember there's a difference between the hydrophobic and the hydrophilic hormones. So the hydrophobic hormones, remember those would be your steroid hormones and also your thyroid hormones. And remember the thyroid hormone, Those are amines, but those are the exception to the amines in that they're hydrophobic. So remember that they don't mix well with the water in the blood, and so they're going to be traveling in the blood bound to the carrier proteins, and then they will fall off, and then they can rebind, and when they do fall off, they can then go bind to their target cell receptor. And then the hydrophilic hormones, they are not bound to the carrier proteins. So these hormones are going to be made out of proteins, and then also the amine hormones. And the exception would be the thyroid hormones, because they're hydrophobic. Remember that when the hormones are bound to the carrier proteins, like the hydrophobic hormones are, that increases their hormone half-life. So they're not going to be metabolized as fast. They're going to be staying in the body longer, and they can only be metabolized or broken down when they're not on the carrier protein. So the rate of hormone metabolism when they're going to be broken down is when they're off the carrier protein, and then they can be broken down by the liver, the target cell, and then there's also some enzymes in the blood. And then there are a few hormones that can be broken down in the kidney too. Abnormal secretion of hormones. We need to make sure that our hormone levels are kept in the normal range. And we've talked about some problems with hormone secretion. So if we have hyposecretion, so too little hormone being secreted. So remember we talked about hypothyroidism, Addison's disease, which is hypoadrenocorticism, type 1 diabetes mellitus, some forms of dwarfism, and diabetes insipidus. Those are all examples of hyposecretion. And then hypersecretion, we've got too much hormone being secreted. So examples there would be hyperthyroidism, Cushing's disease, which is hyperadrenocorticism, gigantism, and acromegaly. And then we could have normal hormone levels, but the tissue may not be responding to the hormone. So we see that in type 2 diabetes mellitus with the insulin resistance. And then we can also see that in diabetes insipidus as well. Okay, hormones can interact with each other, and this occurs when the target cell has receptors for more than one hormone. And there's 3 different types of hormone interactions that you need to know. So these will definitely show up on the test. So we've got antagonism, synergistic effects, and permissiveness. So antagonism is when the effects of the 2 hormones are opposite. So a great example of antagonism would be insulin and glucagon. So remember, both of these are secreted by the pancreas, and insulin is going to decrease the blood glucose, and glucagon will increase the blood glucose. So you can see that they are antagonistic to each other and they have the opposite effects. And then when you have 2 hormones producing the same response at a target cell. So an additive effect would just be when, if you added their individual effects together, it would be like 1 + 1 = 2. Okay, but what we can see is synergism. And what this means is that the net effect of the 2 hormones is greater than the sum of the individual effects. So it would be like 1 plus 1 equals 3. So you're going to get a bigger effect than if you just had added the individual effects together. Okay, so that word synergism, syn means together and erg means to work. So that's what synergism means. So these two hormones have the same, they're going to produce the same response, and you're going to get a bigger effect if they're both there together than if you would just added both of their effects together. So let's give you an example of synergism. So two hormones that are synergistic to each other are glucagon and epinephrine. So they both are going to increase the glucose levels in the blood. So they both will act on the liver. And if you look at what's going on in the liver, notice that they're going to take the glycogen stores in the liver and break it down into glucose. So they're going to stimulate glycogenolysis. And then they're also going to stimulate gluconeogenesis. So they're going to take these things that are not carbohydrates and they're going to make some new glucose. Okay, and then the liver will release the glucose into the blood. So epinephrine and glucagon each will increase the glucose in the blood. If they're both released together, the epinephrine and glucagon together will produce an even greater response and get a much higher increase in the blood glucose than if you had just added their individual responses together. So that's synergism. And then the last hormone interaction is called permissiveness. And this is where one hormone permits the other one to work. So an example here is thyroid hormones. So they stimulate the smooth muscle in the bronchioles to produce epinephrine receptors. So if thyroid hormone is not around, the smooth muscle in the airways will not produce epinephrine receptors. And then if epinephrine is secreted, the airways will not dilate because there's no epinephrine receptors. So thyroid hormones are going to permit the airways to respond to epinephrine because they tell the smooth muscle to make those epinephrine receptors. Okay, so that's permissiveness. One hormone permits the other one to work and have its effects.